Imagine, if you will, a kitchen, not your kitchen at home. This is a cosmic kitchen, a place of infinite experimentation. Here, ingredients are ideas, discoveries are the meals. Sometimes the greatest recipes are found by accident, a spill, a forgotten dish, something left out too long. This is one such story, about a tiny fuzzy oversight, a speck of mold, an unassuming patch of green. It looked like spoilage, like something to be discarded. Yet within it lay a universe of potential. This was no ordinary kitchen mishap. This was science. It began not with a grand plan, not with a thunderous eureka, but with something far more mundane, a bit of carelessness perhaps. A forgotten culture plate in a London laboratory. Think of it like a message in a bottle, tossed into the ocean of chance, waiting for a keen eye, a curious mind to find it, to decipher its hidden meaning, its profound secret. This tiny, moldy patch was about to rewrite human history. It held the key to conquering invisible enemies. The tale begins with a simple observation, almost an afterthought. A scientist returns from holiday, his lab a little untidy. Among the stacks of experiments, one Petri dish stands out. It's contaminated. Mold has bloomed upon its surface. Most would sigh, toss it out, start again, but this was no ordinary scientist, and this was no ordinary mold. He looked closer. He saw something astonishing, something that would echo through the halls of medicine forever. This was a whisper from the microbial world. This moldy sandwich of our story wasn't a sandwich at all, it was a Petri dish. A small flat plate used to grow bacteria, but the principle is the same. Something unwanted grew, and that unwanted guest brought with it an incredible gift. A gift of healing, a gift of life. It's a reminder. The universe is full of surprises. Often the most groundbreaking discoveries are not sought. They are stumbled upon by those who are looking, even if they don't know what they're looking for. Our journey into this medical marvel introduces us to a scientist. His name was Alexander Fleming. He was born in Scotland, a farmer's son. He grew up close to nature. Perhaps this taught him to observe, to notice the small things. He became a bacteriologist, a microbe hunter. He studied the tiny, invisible world of bacteria. These organisms, some harmful, some helpful, teem everywhere. Fleming was searching for ways to fight the harmful ones, to stop their deadly march. Fleming worked at St. Mary's Hospital in London. His laboratory wasn't always the neatest. Some might say it was cluttered, stacks of Petri dishes, glassware here and there, but sometimes a little bit of chaos can be creative. It can open doors to unexpected possibilities, like a slightly ajar window letting in a surprising breeze. Fleming was known for his sharp mind, his keen intellect. He had already made a discovery, lysozyme, an enzyme with mild antiseptic effects found in tears. He was a veteran of World War I. He had seen suffering. He had witnessed firsthand the horror of infected wounds. So many soldiers died, not from bullets or bombs directly, but from the bacteria that invaded their injuries. This experience fueled his quest, his search for a weapon against these microscopic killers. He knew there had to be something, some way to fight back. His untidy lab, in a strange twist of fate, would provide the battlefield for his greatest discovery. Fleming was not a showman. He was a quiet, observant man. He let his work speak for itself, patiently, meticulously. He was part of a grand tradition, the lineage of scientists, those who explore the unknown, charting unseen territories. His contribution would not be a planned invention. It would be a serendipitous observation, a moment of insight. The universe had a secret to share, and Alexander Fleming was the right person in the right place at the right time. Even if his bench was a bit messy. The summer of 1928, a time for rest, for escape. Fleming, like many others, decided to take a holiday. He packed his bags, left his London laboratory behind, but science rarely sleeps, even when scientists do. He left behind stacks of Petri dishes, cultures of Staphylococcus bacteria. These are common bacteria. They can cause boils, sore throats, and worse. One stack was on a bench near an open window. A seemingly insignificant detail, but crucial to our story. The days turned into weeks. Fleming enjoyed his break. Back in the lab, something was happening, unseen, unplanned. A tiny spore of mold drifted in through that open window, perhaps from a nearby lab, perhaps from the city air itself. It was a microscopic traveler. On a journey of chance, it landed right onto one of Fleming's bacteria cultures, a tiny seed of change. Finding fertile ground, the bacteria were growing. The mold began to grow too. A silent competition was underway. When Fleming returned in September, he faced a backlog. tidying up, checking his old experiments. He began sorting through the Petri dishes. Many were as expected, covered in colonies of bacteria, but one dish made him pause. It looked different. It was contaminated with a patch of blue-green mold. His first instinct might have been frustration, a ruined experiment, but then he noticed something truly remarkable, something that sparked his keen scientific curiosity. This wasn't just any contamination, it was special. The mold was there, certainly, a fuzzy circular colony, but around it there was a clear zone, a halo. In this ring, the usually thriving bacteria were gone. It was as if the mold had put up an invisible shield, or perhaps wielded an invisible weapon. "That's funny," Fleming reportedly remarked to a colleague, a beautifully understated comment for a discovery that would save untold millions of lives. Fleming looked closer at that peculiar Petri dish. The mold, a bluish-green fuzz, was thriving, but the bacteria, the dangerous Staphylococci, were not. In the immediate vicinity of the mold, they had vanished. It was like a tiny battlefield. The mold was winning decisively. Further away from the mold, the bacteria grew normally, but near the intruder they were lysed. They had burst. A clear, distinct circle separated the mold from the healthy bacterial colonies. This was more than just funny, this was profound. Fleming realized the mold wasn't just coexisting, it was actively inhibiting the bacteria, it was killing them. The mold was producing something, a substance. This mysterious substance was diffusing into the agar, the jelly-like growth medium, and wherever this substance reached, the bacteria could not survive. It was a chemical warfare on a microscopic scale, a silent, deadly attack by a humble fungus. He was a trained observer. He knew this was significant. Many might have missed it or dismissed it as a spoiled sample. But Fleming's mind was prepared. He had been searching for something, anything, that could kill bacteria. And here it was, dropped into his lap by sheer chance. He carefully isolated the mold. He began to study it. He wanted to understand its power, its secrets. This was the birth of an idea, the dawn of the antibiotic age. He named the active substance mold juice initially, a rather unglamorous name for such a potent killer. He grew the mold in liquid broth. He found this broth, even when diluted, could stop bacterial growth. It was effective against many types of harmful bacteria. The ones responsible for scarlet fever, pneumonia, meningitis, diphtheria. Crucially, it seemed to be harmless to animal cells. This was the magic bullet scientists had dreamed of, a substance that targeted the enemy but spared the host. Section 5. Unmasking the microscopic hero Penicillium notatum. The next step was identification. What was this wonder mold? Fleming was a bacteriologist, not a mycologist, an expert in fungi. So he consulted with colleagues who knew more about molds. He sent samples for analysis. The mystery needed a name. The mold was identified as belonging to the genus Penicillium. Specifically, it was a strain of a common mold. You might find its cousins on stale bread or aging cheese. Yet this particular strain held an extraordinary power. Fleming continued his experiments with this. He confirmed its remarkable bacteria-killing properties. He called the active substance penicillin, after the mold that produced it, a logical choice. He published his findings in 1929 in a scientific journal. He described its potential, its ability to fight infections. He even used crude extracts to treat some surface infections. But the world wasn't quite ready. His paper didn't make big waves, not immediately. The challenge was purification and concentration. Fleming's mold juice was unstable, difficult to work with. Producing enough of the active penicillin was incredibly hard. He was a brilliant observer, a pioneer. But the task of turning this lab curiosity into a usable drug, that required a different set of skills and more resources. For about a decade, penicillin remained mostly a scientific curiosity. A promising substance, yes, but not yet a practical medicine. Its full potential lay dormant. Think of it, a life-saving compound, known but inaccessible. Like discovering a map to a vast treasure, but the map is fragile, the path is treacherous. Fleming had pointed the way, he had lit the first torch, but the journey to bring penicillin to the world, that would require new explorers, new efforts. The universe had revealed a clue. Humanity needed to learn how to use it. The stage was set for the next act in this incredible story of discovery. Section 6, the science of saving lives, how penicillin works wonders. So what is the secret of penicillin's power? How does it defeat bacteria? It's a tale of cellular engineering and sabotage. Bacteria are single-celled organisms, tiny living fortresses. To protect themselves, they build strong cell walls. These walls are made of a special material, peptidoglycan. Think of it like bricks and mortar, holding the bacterium together. This wall is essential for the bacterium's survival. It gives it shape. It protects it from bursting under pressure. Penicillin is a master disruptor, a molecular saboteur. It targets the very process of building these bacterial cell walls. Specifically, it interferes with the enzymes, the tiny biological machines. These enzymes are responsible for linking the peptidoglycan components together. Penicillin blocks these enzymes. It gums up the works. Imagine a bricklayer trying to build a wall, but someone keeps stealing their trowel or gluing the bricks together incorrectly. The wall becomes weak, unstable, full of holes. When a bacterium tries to grow or divide, it needs to build new wall material. If penicillin is present, this process fails. The cell wall becomes compromised. It can no longer withstand the internal pressure. The bacterium swells up and then, pop, it bursts. This is called lysis. The bacterium effectively self-destructs. It's a beautifully precise mechanism, targeting a structure unique to bacteria. Human cells don't have peptidoglycan walls. That's why penicillin is generally safe for us. It attacks the invaders, not our own cells. This specificity is what makes penicillin so revolutionary. Before antibiotics, treatments for infection were often harsh. They could be as damaging to the patient as to the bacteria. Think of arsenic compounds or mercury, toxic stuff. Penicillin offered a new paradigm, selective toxicity. It was like a smart bomb, hitting only the enemy targets. This was a monumental leap forward in medicine. The humble mold had yielded a weapon of incredible sophistication, a gift from the microbial realm. Section 7, from lab bench to lifesaver, the trials of mass production. Fleming's discovery in 1928 was the spark. But turning that spark into a roaring flame of medical treatment took time and teamwork. For nearly a decade, penicillin remained a laboratory curiosity. The main problem was producing it in large enough quantities and purifying it. Fleming's crude extracts were unstable, difficult to work with. He recognized its potential, but he couldn't crack this production puzzle. The world was teetering on the brink of another great war. The need for a powerful anti-infective drug was becoming desperately urgent. Enter a new team of heroes, Howard Florey and Ernst Chain, and their colleagues at Oxford University in the late 1930s. They stumbled upon Fleming's old paper. They were intrigued. They decided to take on the challenge of penicillin. Led by Florey, an Australian pathologist, and Chain, a German-Jewish biochemist refugee, they assembled a dedicated group. They were determined. They revisited Fleming's work. They began the painstaking process to isolate, purify, and test penicillin properly. Their work was arduous. Resources were scarce. Britain was at war. They grew the penicillium mold in all sorts of strange containers, bedpans, milk churns, anything they could find. They needed to extract tiny amounts of penicillin from vast quantities of mold broth. It was like panning for gold, sifting through tons of river mud for a few precious flakes, but they persisted. Their early results were astonishing. They showed that purified penicillin could cure deadly infections in mice. The next step, human trials. This was a moment of truth. The first human patient treated with purified penicillin was Albert Alexander, a policeman. In 1941, he had a terrible infection spreading from a scratch. He was dying. Penicillin brought about a miraculous improvement, but their supplies were so limited they ran out. They even tried to recycle penicillin from his urine. Tragically, he relapsed and died once the penicillin was gone. This heartbreaking case highlighted the urgent need for mass production. The race was on to make enough penicillin to save millions. The United States would soon join this critical endeavor. Section 8, A World Reborn, Penicillin's Monumental Impact. The successful, albeit tragic, trial on Albert Alexander proved penicillin's power. The challenge now was scaling up, from lab bench to industrial production. With Britain under siege, Florey and another colleague, Norman Heatley, traveled to America. They sought help from the US government and pharmaceutical companies. It was a critical mission. The fate of millions hung in the balance. American scientists and companies embraced the challenge. With vigor, they developed new techniques, deep tank fermentation, better strains of mold. One particularly productive strain was found on a moldy cantaloupe in Peoria, Illinois. Serendipity strikes again. By 1944, penicillin was being mass-produced, just in time. It became a crucial weapon in World War II, not a weapon that kills the enemy, but one that saves your own. Countless soldiers survived battlefield wounds, infections that would have been fatal before. Pneumonia, sepsis, gangrene, penicillin fought them all. It was hailed as a miracle drug, and it truly was. The impact was immediate and profound. Death rates from bacterial infections plummeted dramatically. After the war, penicillin became available to civilians. It transformed medicine completely. Diseases that were once terrifying became treatable: scarlet fever, rheumatic fever, syphilis, gonorrhea, bacterial endocarditis. Childbirth became safer, surgical procedures became less risky. Patients could now undergo complex operations. With less fear of deadly post-operative infections, life expectancy increased. The world was a healthier place, all thanks to that forgotten Petri dish and the curious minds that unraveled its secrets. Penicillin ushered in the age of antibiotics. It was the first, but many others followed. Streptomycin, tetracycline, and more. Each new discovery built upon the last, expanding our arsenal against disease. Modern medicine, as we know it, is built on this foundation. From routine doctor visits to life-saving hospital care. The legacy of penicillin is all around us. In every saved life, it's a testament to the power of observation, persistence, and a little bit of luck from the cosmos. Section 9, Serendipity's Gift, the universe's accidental discoveries. The story of penicillin is a powerful reminder. A reminder that science is not always a straight path. It's often a winding road full of unexpected turns, surprises. Fleming didn't set out to find penicillin. He stumbled upon it. It was an accident, a fortunate accident, what we call serendipity. The universe, it seems, has a habit of revealing its secrets in this way, through chance occurrences, through overlooked details, if we are open, if we are observant. Chance, as Louis Pasteur famously said, favors the prepared mind. Fleming's mind was prepared. His years of research, his curiosity, his untidy lab bench, all played a part. He saw something unusual. He didn't ignore it. He investigated it. That's the hallmark of a true scientist, the ability to see significance, to ask why when something doesn't fit the pattern. This curiosity is the engine of discovery. It drives us forward, into the unknown, towards new understandings. Many great scientific breakthroughs have come about by accident. X-rays, pacemakers, post-it notes, even microwave ovens. These were not planned inventions. They were serendipitous discoveries. Someone was looking for one thing and found something else entirely, something unexpected, something wonderful. It's a humbling thought that some of our greatest advances arise not from deliberate design, but from the universe's playful nudges. It tells us to keep exploring, keep experimenting, keep our eyes wide open. The legacy of that moldy sandwich, that contaminated Petri dish, is immense. It's not just about penicillin or even antibiotics in general. It's about the spirit of inquiry, the pursuit of knowledge. It teaches us that even the smallest, most insignificant seeming thing, a speck of mold, a forgotten experiment, can hold the key to changing the world. So look around you with wonder, with curiosity. The next great discovery might be hiding in plain sight, waiting for its "that's funny" moment. Like and subscribe for more valuable info about past gems and current events that can help you in your life and studies. Stay tuned for more.